right, welcome to Module 34. This is going to be a direct sequel to Module 33 when we introduced the idea of vanishing gradients and exploding gradients. We're just going to explore the space a little bit more and talk about problems and remedies thereof. So at the end of today, you should be able to explain what these are and how they show up in training curves, which we haven't actually seen too much of in Module 33. You'll be able to derive a simple one-dimensional or linearized example showing how gradient magnitudes scale with depth. This is actually really connected to Module 33. You'll be able to diagnose unstable training using gradient statistics. You'll be able to compare and justify common remedies, which we hinted at in the previous module. And you'll be able to implement and interpret small PyTorch experiments that illustrate vanishing and exploding gradients in practice. So right off the bat, let's get and scaffold our concepts. We know about gradient flow. We know how gradients propagate backwards from the loss through each layer. We know about vanishing gradients that shrink to zero as they propagate to earlier layers. And we know how that will lead to early layers learning either very slowly or not at all. We've learned about exploding gradients, where gradients will either grow exponentially large as they propagate backwards through the neural network, and this can result in chaotic, destabilized training, where loss spikes, parameters become huge, nans start appearing because we have numerical overflow on our computers and so on. And I've also introduced a couple of papers. These are the same papers from last time, where we talk about initialization and normalization. Actually, here I'm linking to normalization in PyTorch documentation, so you can see how to actually implement this. So here is the visualization I wanted to show you. This is more or less, this is all fictional data, but it shows, there we go, and there we go. It shows a couple of things. We have training steps over here from 0 to 40, so it's very quick training. We have the gradient magnitude normalized as the z-axis going up and down, and then we have our layer index going from input to output, from left to right in both of these cases. Actually, here it's reversed. There you go. So this is a visualization of kind of what we've been talking about. So I think you already had a concept of this in your mind. This shows how gradients change if the gradients are vanishing versus if they're exploding. So here also the scales are different. Here the gradients start being around 1.4, but then as I move to earlier and earlier layers in this neural network, their gradients drop off to 0 and then they stay at 0, meaning that I'm not doing any learning in these early areas of the neural network, as very early on and throughout the neural network, throughout the training process. Here is the opposite problem. Here I start with gradients at the output layers that are maybe close to 1.4 or something reasonable, but then as the scale of my Jacobians become very, very large, and I multiply these things together, then I get an exponential increase in the norms of my gradients in earlier layers here, and then I'm jumping up to orders of magnitude greater changes that I'm making to my parameters theta, meaning that I'm kind of totally like jumping around the loss space and not really learning anything decent. So this is just a visualization of what we've been talking about for quite a while. So one thing that I used to see a lot of in the old days, but I still see a lot today, the old days being like 2019, where that, well, like deep neural networks are so great, and like, these deeper and deeper neural networks can solve harder and harder problems. So if I'm encountering some kind of problem with my accuracy or my predictions or whatever the metric I care about, then what I should be doing is I should add more layers, and the more layers I add, the more capacious or the more capable my neural network will be, and everything will be fine. This is a deep problem. So this is related to something called the scaling hypothesis, which is a fancy way of saying the bigger is better, and it doesn't always make sense. It's kind of silly. So here we have our 3-layer neural network that isn't accurate enough. We're saying, well, if we stack 50 more layers with tan-h and default settings, then everything will be good. And this is silly, as the silly emoji indicates. So we're not paying attention to initialization. So maybe if we initialize with small weights, then the derivatives of those weight matrices will have small numbers, and then that will potentially, when you multiply those together, will vanish your gradients. Our tan and h and sigmoid functions can also have derivatives near 0, which we talked about in the previous module. If you have lots of these tan H's being multiplied together, then that will also, or these derivatives of tan H's being multiplied together, this will also make your activations saturate. And then the result is early layers have gradient norms close to 0, training loss may decrease slightly at first, but then will stall, and then accuracy will stop improving, and like the presumed solution I came up with at the beginning just won't happen. Depth alone will not guarantee better performance. Gradient health is a better way of thinking about learning. Not to say that depth isn't important. We'll see soon enough again, like the importance of representation, and the deeper models can indeed learn a lot more, and bigger is usually better. But you have to be a bit nuanced and understand, again, we have more and more complexity in terms of what we're learning about and in terms of how we're doing machine learning. So it's never just one thing. There's no silver bullet. There's a lot of interacting components we have to be considerate of at the same time. So here's another simplified one-dimensional picture just to make it clear in our heads. We have another deep scalar network just to help with intuition. We actually walked through this in a previous previous module, so I'm not going to spend too long on it. Here we have just a simple variable x, so our hidden variable is going to be h sub 0 initially. We have this linear transformation, no bias, passed through an activation function phi, giving us our hidden layer at layer L and so on. And then we have a loss at our final output. So the gradient loss with respect to the early activation, some early activation early in the network at layer K, will be the loss at L with regards to the output at layer L. Again, I'm going to update some of these variables so that we can differentiate between loss fancy L and output layer big L. Anyway, we know that we're going to have to take a bunch of products together, so it's a product of the derivative at a layer given its pre-activation function times the weight at that layer. And now, because we're dealing with scalars, the weight is just a single variable, w. So we've seen this before, but now we have a nonlinear function phi, thank goodness. So if we approximate the overall scale of the derivative of the pre-activation, the derivative of the activation function given the pre-activation function times the weight matrix W sub L, or the weight W sub L. This is approximately, again, something scalar. So we saw this again, the same logic in the previous module. So if the scale is more or less the same thing, it's always around A, then the scale of the derivative of the loss with regards to the hidden activation at any arbitrary layer, K, in the neural network, will be approximately the scale of the loss with regards to its output times, A to the power of L, big L minus K, so however many layers I have between K and the output. Okay, it's A times A times A, however many layers that is. Same logic we saw before. If the size of A is less than 1, then this will vanish the gradient. If the size of A is bigger than 1, this will explode the gradient. And if the size is approximately 1, then training will be relatively stable. There's a couple of things going on here behind the scenes. So the loss, the derivative of the loss with regards to the output, this depends on like whatever the loss function actually is. So is the loss function a cross-entropy binary, like a binary classification task? Is it a regression loss? Is it something else? Each of these will have a different loss function here in the first factor. And also, like again, I've mentioned this several times already, but here everything's boiled down to a single number A, a single scalar A. But the same logic applies when I'm dealing with big matrices, not just single values W, but big matrices of weights. But these matrices of weights can be characterized by singular values, sigma, and then we talked about that in the previous module. The same logic applies. If those sigmas are very similar to one another, then the same exact logic applies. Actually, here we are. So we have more realistic networks. So we have weight matrices, big W, but everything is the same. So the derivative of the loss with regards to a hidden layer K and its output will be now a product of the transpose of weight matrices times D. The D is the diagonal matrix of activation derivatives from the Jacobian. So we've also seen this last time. I'm just now calling the diag matrices D now. Well, we've seen D in the previous module. And this is a product of each of these weights times the Jacobian, weights times Jacobian, weights times Jacobian. Again, I think some people might not be comfortable with, like, well, what is a transpose? Here, W sub L to the T-ish looking thing. This means the transpose of the weight matrix. And if you don't remember about the importance of the weight of transposes and how they apply to matrix multiplication, then that's not really a focus of this class. We're a little bit above there in terms of abstraction, so you can kind of conceive it as just like a weight matrix times the Jacobian, but like the details, it's fine if you're getting nervous about not understanding that, at least with regards to the pragmatics of this class. So the size of the gradient will be roughly controlled by the product of these norms. So this norm of this product of all of these matrices together is going to be roughly bounded by the product for all these layers of just the norm of the weight matrix times the Jacobian. So if any of these weight matrices times the Jacobian, if you know, on average, if they're all less than 1, then this could end up with vanishing if it's a lot less than 1. If, like on average, the norm of your weight matrix times your Jacobian, and again the Jacobian has these derivatives tied up in it. If it's bigger than 1, then this could lead to some explosions. And what we want is we want to initialize and normalize to make these norms at a layer by layer basis. Again, like the overall behavior here on the left of this inequality can be bounded by the product of these individual norms for every layer. If I can make these individual layer norms be close to 1 so that the gradients don't collapse or don't explode, then I'll be a happy camper or a happy machine learning scientist. So we talked about these patterns already. Here's some papers that we cited already that you can check out. We're going to talk a little bit about them now. So you can choose weight variances. You can choose weight matrices initially that have variances so that the forward activations keep the scale relatively controlled across layers, and then therefore that the backward gradients also stay in healthy ranges. So this basically means controlling the variance of our weight matrices. And you might remember from our discussion not too many modules ago of ways we can control the size of our weight matrices through a particular operation or set of operations. Is normalization, BatchNorm and LayerNorm are linked here. These are when we have our activations and then we recenter them or we rescale them so that these activations have controlled means and variances or controlled covariate shifts. You can think in terms of z-score normalization. So in z-score normalization, you take all of your data and you shift the data so the average of that data is 0 and the standard deviation of that data is 1. Similar logic applies here. We're just applying normalization, but we're doing it step by step, layer by layer. And if you do this correctly, this will allow you to change your learning rates in ways that now make sense and are a bit more independent and allow for more stable optimization. And then residual connections are the one in which we have layers that learn different adjustments. So we have a layer at L plus 1 is some function L at layer L plus some other function of f of L applied to the hidden layer L. You can let the gradient flow along the identity path, one in which there's no products if f of L is problematic. Otherwise, we can use some transformation function f. And these residual connections allow for very, very deep networks. So ResNets were some of the earliest ones that had hundreds of connections trainable. Let's see some examples to hammer this home. So our goal now is going to be to observe how gradient norms at early layers can change with depth and activation. And we're going to see tanh and ReLU networks now. And then we're going to, again, do experiments with neural networks of 2, 4, 8, and 16 hidden layers. We're going to set up our input with random Gaussian data, random norms, normal functions to produce our data. And we're just going to produce these data points without the need for labels. We're just producing random inputs. And then we're going to build random networks, compute the loss, and then inspect the gradients of the layers. So here's the code that does this. This is going to be mostly in Torch now. This is basically the same logic as a previous previous module. I can't help myself. I'm going to have to walk through this in a little bit of detail just so I'm not waving my hands too much. We have another function in the previous module also called makeMLP. This takes a hyperparameter width. It takes in a hyperparameter the number of features I want. It takes in a hyperparameter the activation function I want. And it'll construct a bunch of layers. Initially, I have no layers. I'm going to keep on accumulating more and more layers. So for the depth, I specify first have a linear transformation and then apply an activation function. So I'm just applying, I'm applying to my layers the linear function in line 12, and then either, if tanh, apply the tanh function from PyTorch, apply that as a layer in line 14. Otherwise, if my transformation function, activation function is ReLU, append a ReLU layer. Otherwise, say, I don't know, I only like tanh and ReLUs. So I'm just kind of constantly adding either a bunch of tanh or a bunch of ReLUs interspersed with these linear layers. And then I apply one more linear layer like I did last time. And I'm saying with all of these layers form a sequence. This sequence is codified within PyTorch NN sequential. Nothing new there. And nothing is really new here either. Here's my grad norms. I'm going to make my neural network, and my y is just going to be like a sum of all of my inputs. I have to zero grad out. Like again, I always have to zero grad out. This is kind of an annoying thing in PyTorch, but it's open source. It lets you have to decide to do this yourself, which I guess is a good thing because open source is the best. And then you do your backwards. You get all your gradients, and nothing new here. Finally, at the bottom, here's my experiments. So try a bunch of experiments with tanh, then do a bunch of experiments with ReLU. In each case, try neural networks of depth 2, 4, 8, and 16. In each case, compute your gradients. And in all cases, append to my data my activations, my depths, my gradients, and then just report it in a nice pandas table, and here it is. I have experiments with tanh functions. I have experiments with ReLU. And in each case, I have different depths. And in each case, I'm computing my gradient norms. And like we saw before, if I have shallow neural networks, my gradient norms tend to be big. If I have deep neural networks, my gradient norms tend to be small. And there's a bit of a difference here between ReLU and tanh. So again, so much of science consists of slight contradictions. I'm not sure if this is a contradiction now exactly, but not a contradiction so much, but like caveats or special cases, or the fact that there's no one truth that is uniformly going to be true. In a previous module, I characterized ReLUs as activation functions that solve the problem of sigmoids and tanh having derivatives that were too small. Derivatives that were too small resulted in vanishing gradients, therefore tanh and sigmoid not good, ReLU good. But empirically here, we see that with these deep neural networks with tanh, I actually end up with gradient norms that are quite a bit bigger than the gradient norms I end up with depths of the same size with ReLU, my magic preferred activation function. So I'm mentioning this, I'm highlighting this just to reemphasize that there's general trends that I've hinted at previously when I'm making these kinds of claims, but just like all of science and just like Carl Sagan would say, don't trust authority, run the experiments yourself, and well, with caveats, right? So you listen to authority when it makes sense, but always do the experiments yourself, and so on. I feel like getting to a bit of a side note, so I'm going to do that now. I'll try to be brief. There's I think the 80s, 90s, the early 2000s, there was a lot of discussion about the fact that, it's a good idea to be skeptical of experts, of authority, and because authorities would come down and say, this is the rule, you have to believe me or you have to obey. And the scientific response was one of rebellion, which would be like, I don't believe that the sun goes around the earth. I don't, believe that, the moon is made of cheese. I'm going to do my own experiments, and I'm going to confront your authoritative claims. Unfortunately, in recent years, there's a situation where conspiracy theories have taken on that kind of idea from science. Science can be rebellious and say, I don't believe what you're telling me, you authority from Health Canada or the CDC in the country to the south of Canada. And that is a perversion of the scientific process. The people we had heading up the CDC and Health Canada weren't perfect. But generally they knew a lot more about disease and epidemiology than any of the rest of us did. So automatically discounting what the experts at Health Canada were saying during a pandemic, for example, to say that you're going to do your own research on Reddit or Google or whatever conspiracy website you happen to go to is like a perversion of what I was just saying. So usually, like just because some expert says it doesn't mean it's true. That is an important thing to remember, but you should also factor into the fact that, the what I called well, I don't think I called it, but I think I might have mentioned the Dunning-Kruger effect, where people who are definitely non-experts think that they're experts, and that can lead to all kinds of problems. Don't do that. Close parenthesis. All of that was just to highlight this this problem I was seeing, or this unexpected phenomenon that the data is telling me that the grad norm for deep ReLU is going to be a lot smaller than the grad norm for tanh deeply. Thank you for, no one's here to yawn or tell me to stop yapping, but I wanted to mention that because so much of this class is in the context of doing science properly, so I wanted to just correct a thing I might have said. That might have been confusing. Here is the gradient norms of just the first layer versus the overall depth of random networks, randomized networks for ReLU and tanh respectively. So here's, like, on the x-axis is how deep the neurons are, but the points are the gradient norms at the first layer, right? So down here, like, is not the gradient norm of the 16th layer, is the gradient norm of the first layer for, I guess, both tanh and ReLU. Both of these cases have a problem of vanishing gradients. Actually, I should make sure I'm not stepping on your toes. Does the gradient norm shrink as the depth increases for tanh? So at the earliest layer, layer 1, does the gradient shrink as depth increases for tanh or for ReLU? Is ReLU more stable? Does it have less shrinkage? When does it have less shrinkage? When does it have more shrinkage? Look at this graph and try to make some reasonable claims qualitatively about the behavior of ReLU and tanh and the depth of these neural networks. So this first example, even if we did initialization, activation choice and depth obviously strongly influence gradients. We knew this to some extent already, given our expectations and given our theoretical mathematics from the previous module. If we see gradient norms that are close to 0 for deep neural networks, gradients vanish. If they're very large, they explode. Actually, I'd advise you maybe to go back to the code and try to fiddle with it until you can make these gradients explode instead of vanish. See if you can accomplish that. The simple diagnostic would be used before we actually do full training. So you could sometimes precede an architecture you have with random data to see if there's something wrong with your architecture. Here's a second example. Now we want to see how weight initialization scale can affect gradient magnitudes in a deep ReLU network by itself. Our plan is to fix, we're only going to look at ReLU now. We're only going to look at 10 hidden layers now, so we're not going to modify those anymore. We kind of have some sense of how they behave on random data. We're going to have 3 different standard deviations for weights. We're going to have initialization of our weight matrices where the standard deviation is going to be very small, close to 0.01, a bit more reasonable, at least for this setup, of 0.1, and then one that's too large, a standard deviation of 1. Okay, so when you create our weight matrices, we previously let PyTorch do it for us, but we're going to do it by hand now. And then we're going to measure mean gradient norm across all linear layers like we've been doing previously. So here, again, now I'm going to control myself, and I'm not going to mention too much. I'm not going to walk through everything because so much of what is in this code is exactly the kind of code we've seen previously. The main thing I want to mention here is that when we're constructing things, now if we have these linear layers, we're going to make our weight matrices initially normal with mean 0, and the standard deviation is going to be whatever we're passing in, whatever we're specifying. Here, sorry, on line 13. So the standard deviation we want is going to be an experimental hyperparameter. We're going to pass it in, and then we're going to kind of construct our weight matrices so that they have these different standard deviations. And then we go ahead and train. So here we do our experiment for a standard deviation, like these weight matrices with standard deviation 0.01, 0.1, and 1. Compute your gradient norms and then see what happens to your neural network. We're not going to be doing full training here. This is just like a simulation of what would happen during training. I think it's important to mention, but everything else here is as it was before, so we're still computing our average gradient norms. And as you probably expect, if we have small standard deviations in our weight matrices, our average grad norms will be very, very small, e to the minus 100 or 10 to the minus 100. If our standard deviations for our weight matrices are relatively big, like 1, we'll get on the order of billions in terms of our gradient norms. So massive changes to our weights, whereas there's some sweet spot over here at 0.1, where we have like a 0.7 average gradient norm, so we'll be adjusting things in a reasonable amount. Again, this is simulated. I'm not using 2 moons or any other real data set. I just wanted to show you that the way that we initialize our standard deviation of our weight matrices can have a big effect on gradient norms. Here's nothing else. Here's just like looking at what we just mentioned before. This is on a log scale. If you were to run this not on a log scale, if you're going to just plot it with the actual values here instead of the log values, you'd see that the weights, the gradient norms for weight initializations of 1.0 will be off the chart. They'd be in the billions, and everything else would be just nothing. So look at some questions. What happens if, I'm not really asking you questions here. Talk about what would happen if your standard deviations of your weight matrices are very small, if they're medium, and if they're large. And if you want to look into schemes on how to initialize your weight matrices in a principled manner, here's a good paper for learning that. So that's it. In summary, I wanted to talk mostly about just kind of one way to avoid vanishing gradients, and we've just done that with the initialization step. So again, big picture, you're in charge of training a deep neural network for a classification task. You want stable training, and you want reliable generalization. So you already know a lot of the tricks. We've talked about them a lot throughout this course. The first diagnosis you might look at is the training curve loss. So if it's smooth, and as you're training over multiple epochs, multiple iterations, you have a more or less smooth monotonic decrease in your loss. This is good. If there's sudden oscillations or spikes or not in numbers or things just breaking, bad, obviously. You look at the validation loss, maybe the accuracy on a validation set. The training loss should also decrease. It might decrease more slowly or be a bit worse than the training loss. But if it plateaus or if it suddenly gets worse, this might be an example of several things. It could be underfitting, it could be overfitting. You might be optimizing a parameter, so you want that to happen at some point. But if it's happening too soon, if like if your generalization fails early, or if your validation loss kind of plateaus or gets worse very early, this might be an indication that you're not actually learning anything. You're kind of underfitting, and you're underfitting because you're only really training things in the layers close to your outputs. So this is where you open the black box a little bit. You start tracking gradient norms per layer. There's ways to do this in PyTorch, which we've seen in our examples. If we've seen the norms going close to 0, they're vanishing. If they're getting big, they're exploding, just to hammer that home a bit more. And this can result in learning rate sensitivities, right? So if you have a very small learning rate, so if you have if you have to change your learning rate eta to be incredibly small just to learn anything, this can mean that your gradients are exploding, and they're exploding because you haven't conditioned your weight matrices appropriately yet. If you had only done the smart thing and set your initial weight matrices to have standard deviations which were appropriate, which were in the middle range, whatever that is, in our example a moment ago, that was 0.1, but different data sets might need different initializations to get the weight matrices initialized appropriately. But if you've done that, then your gradients wouldn't explode, and then therefore you could have more flexibility with regards to your training rates eta. So generally, there's a couple of things you can do. I know we ran into this problem a few moments ago with regards to using ReLU compared to tanh, and that kind of seemed to contradict what I normally expect to see happen. But again, it's science, so it's not a bad thing. There's no single truth. We're always just trying to find the truth. Use an activation function that could avoid differentials that are very small. Use initializations that are good for your weight matrices. Add residual connections, which we'll talk about a bit later, and consider LayerNorm or BatchNorm, which we'll also see in our code coming up shortly. We didn't have time today, but there's mitigations to normalize. normalize everything so that backpropagation doesn't explode or vanish. Also, you can also have optimizers which are robust. We had a whole module on optimization. We talked mostly about stochastic gradient descent. We talked a little bit about momentum. We talked about adaptive momentum, as is the case in Atom. We didn't talk too much about Atom. We had a slide where we showed some mathematics as an aside, but there's ways of using optimizers that can flexibly respond to problems that come up with your gradients. You can't rely only on Atom to solve all of your problems for you, or like any other fancy optimizer to solve all of your problems. Again, there's lots of knobs you have to turn. But there are lots of again, there are knobs that you're increasingly aware of to help you do training appropriately. A bit of curiosity, again, these are not going to be, I'm not going to quiz you on Shao et al.'s paper on dynamic isometry and a mean field theory of recurrent neural networks. We haven't even talked about recurrent neural networks yet. Yeah, all of this issues of gradient propagation come up quite a bit in the theory, more theory of signal propagation. They come up in the diagnosing shattered gradients. This is a nice paper that talks more about that, and papers that go beyond like normalization. So again, the concepts we introduced here come up a lot in really decent papers that you should check out if you have that curiosity. Some quick checks. Oh, sorry, I'll make this small. So again, you're going to start training a neural network. Have you chosen reasonable initialization? Have you chosen initial reasonable activations? Have you used BatchNorm and LayerNorm like we hinted at? Have you inspected the gradient norms per layer to make sure that they behave in a sane way? And do your loss curves look healthy generally? If any of these things fail, you might have a vanishing or exploding gradient problem. Here are awesome references. As usual, thanks so much. See you next time.